fast as well. So as promised earlier, let's first look into the NAND cell and what does it constitute of, how does it work? Because a NAND cell is the smallest, it's a transistor that's responsible to store single bit, 0 or 1. And just there's many of these NAND cells that individually stores a single bit eventually constitute this monster large capacity SSDs, right? So let's first start our understanding from that smallest granularity of data, how it is stored, and how do we store 0, how do we store 1, how does it relate to the physical component of NAND transistor. So does anybody remember what is the table of NAND? Well, I hope you do. And if not, then that's something your fingers would be already typing now to Google that. Okay, so I trust your Google search skills to find that table of NAND dependency of input and output. Here, what we are looking at on the screen is a NAND transistor, which has the control gate, the input to the control gate, then the insulator, the floating gate. Floating gate is responsible to store charge, and thus it makes the persistence, it gives the persistence property to the cell. We have our silicon substrate, this one, which has its source, its drain, and then we have, depending upon the current that we apply at source and drain, either the current flows in the silicon substrate or it does not flow. And depending on if the current is not flowing, as we see here in this figure, if the current is not flowing, that means the electrons can gather in the floating gate, which gives it one state. We could call that as 1. 1 means in terminologies of SSDs, again, having 1 means it's a clean state. Just after an erase, all the bits would be 1. Now, when we apply particular certain currents to source and drain, then current electrons would flow in the silicon substrate that would lead to the drain of the electrons gathered in the floating gate through the insulator. And over time, over time, this insulator that's separating this electron channel of silicon substrate and the floating gate, that deteriorates. And with that deteriorating, what we are losing is the capacity of the floating gate to hold electrons, right? As what it is holding in this first figure. And this is exactly the reason behind limited number of write program erase cycle of every NAND cell. It depends upon this degradation over time through which the charges accumulates, and eventually we would be at a stage where we wouldn't be able to flip or differentiate between electrons stored versus electrons not stored. And that's the state where this NAND cell is no more usable. So here we are looking at SLC. In SLC, as I just showed in the diagram, either we are storing 1 or we are storing 0. So SLC is responsible to just store a single bit, 1 bit. And that's why it is also one of the best kind of material that with which we can make an SSD. By best, I mean it is most reliable because we are not densely packing the data inside the transistor cell. But this reliability also would cost us. So it is costly. it occupies more space because the density at which we are packing the data with respect to the physical material is very less, only 1 bit in 1 transistor. So it occupies more space. So this SSD, SLC SSD could look big for a certain capacity. And but it gives us better performance. In sense, SLCs perform much better. It gives more reliability, but at the cost of high cost and at the cost of the, what is the last one that I said just now? More space occupancy. Yes. So good performance, good reliability. And well, it is high cost still, but high cost is not a good thing. And large space, so still high space occupancy. But these both are not good things. These both are good things. Okay, moving forward. Now, you might be already thinking that if I mentioned and emphasized about that single level cell, there must be more coming, right? There must be more variants, and that's why we are discussing one of its variant, which is single level cell. So yes, your thoughts are correctly aligned. There are more variants. Another popular variant is called multi-level cell. In multi-level cell, now instead of storing 1 bit, we can store 2 bits inside a single transistor. So we can imagine that if we are storing 2 bits, we can store 4 states of data, 0, 0, 0, 1, 1, 0, 1, 1. How do we store these, or how do we identify or read and write these 2 bits? It depends upon how much the density of electrons that are gathered inside the floating gate. As we see here in this 4 state illustrated in this figure, we see first that if there is no charge in the floating gate, that could be called as state 1. We can say that our 1, 1 could represent as state 1. Now, if there is, or let's say, if there is no electrons, that means it is positive, right? Electrons are responsible for a negative charge. So we can say our 0, 0 is our state 1. Just to be simplistic, let's go top down. So 1, 1 is state 4. This is state 2, state 3. So when we have few electrons gathered into our floating gate, then we can say that, well, it's slightly negative, and that could be our state 0, 1. When we have few more electrons, we can say it's medium charged, and that can be our state 1, 0. And we have floating gate full of electrons up to its highest capacity, then we can say that it's fully charged or highly charged, and that can be our state 1. That can be a representation of our state 1, 1. And in this way, depending upon how many electrons is a floating gate holding at any given time, we can, by controlling that, we can control whether we are storing which bit 0, 0, 0, 1, 1, 0, 1, 1. And once we are able to do this, definitely we can successfully write. In order to write, we would have to store that many number of electrons inside the floating gate. In order to read, we are just identifying how many electrons are stored inside the floating gate and responding towards whatever notion of correspondence of bits to the electrons stored in the floating gate is. Now, apart from multi-level cell, in addition, we also have TLC SSDs. These TLC SSDs store 3 tri, as T stands for tri. It stores 3 bit inside each transistor. We won't be discussing or having an elaborated discussion on showing each state, because it's on the same lines as what you saw earlier for the MLC. So exactly by just controlling further granularly controlling the amount of electrons that are stored inside the floating gate, we can transition the same transistor cell into a TLC, and we can differentiate. In TLC, we can differentiate stored 3 bits, so we can differentiate across how many states. With 3 bits, we would be able to get 9 states, right? 1 to 9 over here. So in this graph over here, we are showing SLC, MLC, and TLC on the x-axis, and y-axis is the total voltage. So depending upon the total voltage cell capable of storing, at what if we are reading, then let's say if the voltage that we read is somewhere around here for SLC, we would say that, well, it's storing bit 0. If the voltage we read is somewhere around at the same location, for MLC, we would say that it's storing 0, 0. But for a TLC, we would say that it's storing 0, 0, 1. In this way, we would be able to read the data, and vice versa in order to write the data, depending upon our differentiation. So we have our pre-known differentiation for each type, right? Like these both for the TLC over here, and over here for over here, and over here for MLC, and so on and so forth. With this differentiation idea, like prior idea of this differentiation, we can exactly store number of electrons inside the floating gate to represent that exact data. So why this variance of SLC, MLC, and TLC matters? As I said, SLC is the one that gives us the best performance and reliability, MLC a bit lesser than that, TLC a bit lesser than that. But on the other hand, on the positive side, SLC is more costly, it occupies more space. MLC is a bit less costly, occupies a bit less space, because now we can store double the amount of data, right? Instead of storing 1 bit, now we can store 2 bits inside the same transistor. And TLC is even less costly and even less space occupying, or even smaller, because now we can store 3 bits of data in that same transistor. So how does this translate to its performance? In this table, we see that the latencies of, we can compare the latency of SLC, MLC, and TLC in the rows, and we can see how specifically their read, program, and erase performance could vary. So as we see, definitely one trend that we are able to see clearly here is that arrays is the most costliest operation, or the operation that takes most amount of time. Then program and then reads are really, really quick for all 3 of them, SLC, MLC, or TLC, irrespective of what technology of SSD we use, but still this trend of arrays most costly, then program, and then the read are the quickest, that applies. But when we compare the trend across SLC, MLC, and TLC, we see for all these operations, for read, program, and arrays, for each one of them, we see that the access latency of SLC is the smallest, then MLC, and then TLC. And it's quite obvious, right? Because if we pack more content inside the same transistor, then definitely we are doing more efforts to read and write things from that. And this more effort somehow translates into this higher latency. So all these small NAND cells or flash cells, they get together to construct this flash-based SSD. And that's what we say, flash to flash-based SSD. Now, apart from this NAND cells or multiple, a bunch of flash cells, what an SSD consists of is, It has its own on-chip DRAM. It has its own SSD controller, and obviously some reading and writing bus that is used to connect this SSD to the other parts of the system, right? So, well, same as advanced hard disk, even SSDs are a small computer of its own. It has its own processing power, its own memory, and its own storage. Now, looking more granularly into what SSD consists of in each of these components, inside the controller, we have the controller manages different bus and channels. Controller is also responsible for performing FTL, flash transition layer tasks, translation layer tasks. And we would soon discuss about each of these tasks in detail. So hold your horses, right? But inside this black chip of flash that we saw over here in this figure, inside that chip, what do we have? That's a package. We can call that, we can say that black chip that we are seeing, that's a package. Inside each package, we have multiple dies. Inside each die, we have multiple planes. Inside each plane, each plane has its own resistors, and it consists of multiple blocks. And as we already know, each block has multiple pages. So just imagine the hierarchy and the parallelism that you exploit because of just the architecture of this hierarchy, right? We could definitely, because each die is independently connected with its own channel, we can definitely exploit channel level parallelism, where we can issue different IOs to different dies. Again, there are some restrictions on if we can issue simultaneous reads or writes within the planes of different dies. If you are interested, definitely feel free to dig more. And I would be most glad to help you with where to dig more. If you are interested, please shoot me an email to know more about how to exploit these parallelism. But with the interest of time, at this point, we would skip those details to discuss in this lecture. But definitely with this idea of hierarchy that we have inside each flash chip, each flash package, and definitely we have multiple flash packages. So it gives us the clue that how, if we use this hardware correctly, what better performance that we could get out of that. So next, let's study about the FTL tasks and what are the operations that FTL is responsible for, what are its duties, how each of the tasks are performed, such as mapping management, garbage collection, wear leveling. These are the three main tasks that FTL is responsible for, and these are three very critical tasks to perform inside the SSDs. And we would look into like why each of this is important, what are the variants of each of this, and who knows, tomorrow you can design a better variant, right? And we can write a research article together out of that came as a product of this course that you took. That would be so awesome. So let's first briefly understand write amplification factor. We did discuss while we were looking at the challenges that SSDs provides, but this figure illustrates a very detailed example. So let's start at this stage where our block consists of 3 pages. It has 2 free pages, and we get this 1 page of changes. So what we can do is, because anyway we have a free page, we could put these changes into this free page and just mark the older version of that page as stale, as we do here. So we could also call stale as invalid, which I would be using interchangeably moving forward. Then at this stage, if 2 new pages arrives, well, in this block, we do not have space to accommodate that 2 new pages in the state as it is, right? Because we just have 1 free page. So one of this new stuff could go in there. But as we know that we cannot overwrite data in SSDs, so we cannot just write another page of new stuff over the stale page, but we would have to erase this whole block in order to reclaim the space that is being occupied by this invalid or the stale page. Thus, what we do is we read all the valid pages, everything that matters to us in this block, take a new block, place all that things that matter to us in this new block, and now this new block will have 2 free pages. So we can add this new stuff to that 2 free pages. And what happens to the old block? Well, we can erase the whole old block and reclaim the whole block as all the pages inside it is free, now ready to store new data. So at the end, we would have this 1 block which stores the things that matter to us from the old block along with this new stuff. And we would have 1 fully empty block which we can use towards storing another data that's coming. In this whole process of how we are handling data inside an SSD, if you would have observed, we are performing internal writes. And these writes are the product of just how we are managing the data inside SSD. They are not the writes that are issued by the application. Here in this example, this additional internal writes are of this 4 pages that matter to us in the page that we want, in the block that we wanted to erase. So we copied that to a new block. So the 4 pages are the internal writes that we are doing. So what we call write amplification factor is the amount of data actually returned to NAND flash. In this case, definitely we are writing the data that application is issuing. So application writes plus internal writes. That's the total amount of writes that we are doing on the NAND flash divided by amount of data returned by host or by application. So that's actually what we are supposed to write, but we are writing something more than that, and that's where this signifies the amplification, as we call it as write amplification factor, or WAF or WA. You would find these terminologies in different research articles named differently. So now with this concept of understanding write amplification into our pockets, let's move next towards understanding the 3 main operations of FTL, which is mapping, garbage collection, and wear level.